encrypt everything, compute anything. At Arcium, our mission is to enable everything to become encrypted, while at the same time allow for anything to be computed over that encrypted state. And so, hi, I'm Yannick, co-founder and CEO at Arcium, and today I want to introduce you to what we are building with Arcium. We're building the first parallelized confidential computing network, and our plan is to usher in a new era of data protection, data ownership, and trustless execution. Confidential computing allows for data protection by protecting data in use, essentially allowing encrypted data to remain encrypted while computations occur over that encrypted data without having to decrypt it before. And so decentralized confidential computing really is a transformative shift, both for the blockchain sector, but also for traditional computing. If we have sensitive data, for example, let's imagine sensitive patient data that is distributed amongst hospitals or healthcare entities. What we are able to achieve with decentralized confidential computing is a unification of isolated data under a single shared function with predefined rules while maintaining privacy. So that means that with decentralized confidential computing, one can train AI models across those isolated data silos and gain new intelligence and insights without compromising any involved party's privacy. Everyone still remains the owner of their data, nothing has to be shared, and nothing actually can be leaked because the system is trustless. But this transformative shift even goes beyond that. It also entails building out a secure execution environment that can be used for arbitrary computations to be executed in an outsourced cloud-like environment without having to trust any single third party. And so the evolution of confidential compute really boils down to a movement away from trusted systems, just as we are doing with blockchain, towards cryptography-based systems. And the go-to solution has always been, for many years, trusted execution environments, TEEs. And they are dedicated hardware provided by trusted third parties. And the issues that we've seen with those systems, relying on those systems, also heavily relying on them in the blockchain space, is starting with complex practices of building secure systems in those architectures, high costs of maintenance and hardware, and significant performance overheads. But those problems are insignificant to the major issue, which is an inherently flawed trust model. Because trusting those trusted execution environments means ignoring the myriad of exploits, vulnerabilities, and attacks we've seen over the recent years. Hundreds of attacks. Also, entire blockchain ecosystems relying on those systems for their privacy guarantees, getting the entire data leaked. And so, relying on such systems, what we need to understand is that means trusting an entire linear supply chain consisting of many single points of failure. And an attacker targeting a single of those points is able to let this entire house of cards collapse. And so the logical solution would be to look for cryptography-based, trustless systems, and zero-knowledge proofs come to mind, allowing a prover to convince a verifier about the truth of some statement without having to reveal that statement. Essentially, the verification of information and execution over that information without having to disclose the information. However, these kinds of protocols still require some party to have access to some highly sensitive plaintext data. And what we're trying to achieve is to build some autonomous execution environment where computations can be securely outsourced and collaborative actions can be taken, which by default with these kinds of protocols is not possible. And so the next innovative protocol one might look at is fully homomorphic encryption, allowing for operations to be performed over encrypted data without having to decrypt the data. While very innovative and promising, on a practical front, we see severe limitations of that technology. And that boils down to an enormous performance overhead in practical applications. And so less complex operations can have a many orders of magnitude slowdown of maybe 1,000 times, but more complex applications in the AI realm, for example, can regularly bring a 10,000 times slowdown and above. And so the decision for developers really boils down to how valuable is data protection and privacy, and more often than not, the more real-time, fast executing technologies, like, for example, trusted execution environments, will be selected. And additionally, we've seen problems and additional costs and performance penalties arise from a requirement for regular bootstrapping operations. And additionally, this kind of technology doesn't allow on its own for selective disclosure. So no information can directly be revealed about encrypted state. Only encrypted state can be produced. But when building those decentralized systems, we might want to have a settlement of transparent information that is the output of such computations. And so combined with the inability to run verifiable compute directly with those protocols, the logical solution for us has really been to look at secure multi-party computations and make that the technological cornerstone of our architecture. And so secure multi-party computations allow a set of participants in such a computation to jointly compute a function over distributed private data without having to share any of that data, while being able to gain shared insights and produce shared outputs of that computation. And a core principle used in multi-party computations is secret sharing. Essentially, secrets being divided, being split into secret shares and distributed amongst the players in such a multi-party computation. And then those secret shares can be used in the multi-party computation to perform local operations and communication-based operations. And at the end, those secret shares that are random encrypted shares that give no information about the original secrets from which they stem can be put together in order to produce an output that can be a plain text output that reveals information, but can also be just encrypted output. And so for us, this technology really builds the cornerstone, and we extend the technology with threshold encryption, allowing anyone to encrypt data for a threshold of participants in such a computation to process. So multi-party computations have trust involved, and there's essentially two kinds of trust models. There's the honest majority trust model for these applications and the dishonest majority. The honest majority trust model is something that we almost likely know from Byzantine fault tolerance, practical Byzantine fault tolerance. For example, more than half of participants in a computation being required to perform honestly for the protocol to function. In this case, it would be for confidentiality to hold. For us, that's not a good enough trust assumption, because trust has to be minimized as much as possible. And so instead, we opted to go for the dishonest majority trust assumption, which allows us to only put the trust in a single player, and not a specific single player, but anyone participating in the computation could be that single player. It just has to be one participant that is not collaborating with all the others to undermine confidentiality in an arbitrarily large set of participants for such a computation. And so what we're doing with the Arcium network is we combine multiple different protocols together and are able to achieve dishonest majority trust assumption across those protocols and utilize semi-homomorphic encryption for a subset of the operations, and for increasing the efficiency for other operations, we make use of recent advancements in the space of pre-processing based MPC protocols, which means that we're using a kind of protocol that splits the computation into two phases. A pre-processing phase that happens independently of the actual computation that is being executed, and the online phase, which is the exact execution of the algorithm that should be executed with the corresponding inputs. And by being able to split those computational parts, we're able to bring the online phase very close to the plain text execution speed. We combine all of this with censorship resistance and guaranteed execution by adapting this pre-processing phase with a commitment scheme that allows all of the participants in the network to identify cryptographic misbehavior by any player. And this cryptographic misbehavior in our stateless computational network can then, by including existing blockchains as consensus and state layers in our network, be used as a proof to penalize misbehavior and guarantee this execution. And so non-participation and misbehavior can directly be punished. And so this permissionless network of computational nodes is clustered into computation clusters with the dishonest majority trust assumption. And those are then associated with execution environments that any developer can utilize. And those execution environments actually exist as virtual encrypted environments on those existing blockchain networks. And they maintain an encrypted persistent state that can be used as input, but also as mutable state in those multi-party computations. And the entire orchestration of computations occurs in a parallelized mempool, which means that since this network is entirely stateless, we are able to run the computations in parallel. So there can be very complex, very costly operations be running for hours while not blocking any execution of other computations, since there's no sequencing, no shared state that needs to be accessed. And the only limiting factor here would be communication overhead for the corresponding computation clusters. And so with this technology, we're able to represent all computations with our protocol. And by focusing on building a purely computational network, we're able to build confidential applications on-chain for different networks. Those networks simply, in those networks, one simply builds a smart contract which accesses one of those encrypted execution environments, and computations that are being ordered in those environments get picked up by our network and are then being processed in this network, and a verifiable output is sent back to that smart contract, allowing for further workflow design. And so you can wrap existing smart contracts in the form of confidential smart contracts, which then turns Arcium with this censorship resistance mechanism in this autonomous execution machine. But what's important to realize is that the network itself doesn't have any notion of what a smart contract is or what a public key is. The network itself is just a sole computation network. And so that allows us to represent any computation, order any computation to be executed in that network, not limited to some smart contract interactions. And so one use case that we've been working on for quite some time now is to be able to, for example, allow confidential AI in our network. And so what has previously always been the issue with confidential AI is the problem of representing floating point operations within this sort of constrained execution environment of arithmetic circuits. And for us, we increased the numerical stability to above 7 decimal digits of precision. And on top of that, we are running this hybrid approach of being able to run real number evaluation, Boolean circuits, arithmetic and garbled circuits at the same time. And by running modular lifting with truncation, we are able to remain in the real number representation. And we don't have to switch between representations that are happening virtual virtually in a different number format. And combining this with approximation of the sigmoid function using Fourier series, we are able to bring this very rapid execution for machine learning within the MPC setting. And so that applies both on the prediction, but also on the training side of things. And that really allows us to close the circle, to be able to, on the one hand, provide federated learning, but on the other hand, also allow for confidential prediction. And so what I want you to take away is that we are pushing for confidential interactions both on the blockchain, but also in the enterprise space, all utilizing this technology. And for us, it's not about building something for blockchain's sake. For us, blockchain is a stack of the entire technology that simply makes sense and is this perfect fit for secure multi-party computations, because it allows us to introduce trustlessness and this improved censorship resistance. And yeah, that's all. Thanks for your attention.